Then first of all, I would like to thank you, Vincent, for inviting me and starting this nice talk, this series of talks, which is very pleasant so far. And in this talk, I will talk more about ion migration in Halide perovskites, opportunities and challenges. I'm kind of following up on the talk from 2 weeks ago as well. So halide perovskites are a class of material which share the same crystal structure, namely ABX3, whereas we have a cation, which can be organic or inorganic, which is surrounded by an inorganic framework out of octahedrals, which are typically lead and halides in the X side. And this class of materials has seen the fastest increase in efficiency which we have ever seen for any solar cell material, which is illustrated here on this figure on the right. Whereas in less than 10 years, these perovskites have reached power conversion efficiencies of more than 25%. To bring this into a context, for silicon, it took more than or almost 40 years to reach this goal. But unlike classical inorganic semiconductors, these perovskites are mixed ionic-electronic conductors, which means that these ions can migrate during the device operation, which is illustrated here with a schematic which is adapted from this paper, which references down here, where in the case of a vacancy within the crystals, for example, these ions can hop from one state to another. And this drastically complicates device measurements, for example, and also leads to the degradation of the device. And in this talk, I'm going to show you how we can quantify this ion migration with capacitance measurements. I will then show you how we can distinguish between ionic and electronic defects using transient techniques. And then I will discuss a bit about the opportunities of this mixed ionic-electronic conductivity. So first, a few words on capacitance measurement. So what is a capacitance measurement? In a capacitance measurement, one applies a time-varying voltage or electric field and measures the current response, which is illustrated here. And then one defines an impedance value set, which is indicated here, and is given by the formula below here. And then one splits this into a real and an imaginary part, whereas one has and total amplitude, which is the amplitude of the measured signal, and the total phase angle, which is the phase delay between your applied voltage and the measured current. And this impedance can then be attributed as a capacitance, which is again given by this formula here, where again one typically has a real and an imaginary part of this capacitance, which is directly related to the dielectric permittivity of the material. And what would we expect now if we measure some kind of material which has a certain process with a certain time constant? This can be called as the debye, not the debye, a certain time constant. And this can be then expressed as this frequency term here with a real and an imaginary part. And this would have this shape as can be seen below. So in the imaginary part, one would have a peak. And in the real part, one would have a step function. Whereas at the low frequencies, one clearly measures this contribution, whatever this contribution is. And at the high frequencies, one cannot measure it because it's too fast, the measurement technique. So we would expect something like this for any process with a certain time constant. One can do the same when looking at the time domain. By simply using a Laplace transform of the frequency domain, and we get this expression where we now have an exponential decay of this certain time constant. And so what I'm showing you here is on the left and on the right graph is exactly the same data presented once in the frequency and once in the time domain. And this is what we are going to look at a bit more detail in for the case of perovskites. But first, let's look at the schematic illustration of band energies in a typical perovskite solar cell material, or any solar cell material for that matter, where we have an anode, we have a cathode, and then we have some blocking layers or transport layers for holes and for electrons. And then we have our semiconductor layer, our active material in the middle. If we now bring these together, we would have a situation something like this, depending a bit on the doping density of the material. We would have, for example, a depletion layer within the semiconductor. And then if we have a more low doped semiconductor, this line would be rather more flat throughout the whole semiconductor layer. But now in the case of perovskites, we also have mobile ions. And these mobile ions will now accumulate at the interfaces of the perovskite layer to partially screen out the internal electric field and also slightly change the interfacial, the band diagrams at the interfaces, which then can be often expressed as a so-called debye layer, which is as a term borrowed from electrochemistry, often used to quantify these changes in band profiles in electrolytes. So in these perovskites, we have now both. We have a depletion layer, depending on the dopant density, and the debye layer. And what we do in impedance spectroscopy now, we have the cell in a state like this, for example, and now we slowly, we apply voltage modulation and measure the current response. So what we do is we measure these ions wiggling around within the cell. And this is, for example, now shown here, where we see what we expect. We have a step function in the real part of the capacitance and a peak in the imaginary part of the capacity. Whereas at a high frequency, we again see a drop off, and this is related to the contact of the material. But what we are mainly interested is the low frequency part, where this is often associated to the ion migration within the material. And we can now come up with a formula if we assume that this is now due to the diffusion of mobile ions within the perovskite layer. We can say this frequency is related to a time constant, which is then related to diffusion, whereas the diffusion is directly related to the distance and the time. And this, without going into too many detail, how this, what this length and this diffusion depends on. This is dependent on activation energy. So what we now can do is we can measure this process at different temperatures, as shown here, fit the data, get and calculate an activation energy, which is, for example, now shown here. And in this case, this would be an activation energy of about 130 milli-electron volts. Now, if we go back to this schematic here and see what would we do now if we want to measure the same process in the time domain. So ideally, we start off with a scenario like this, where we have applied a bias, which is more or less the built-in electric field. So we have flat band conditions. And then in the case there are any mobile ions within the perovskite, these mobile ions would redistribute due to diffusion until they are more or less homogeneously distributed within the perovskite. Now, if we go back to this scenario, if we now have these mobile ions within the device and we now have a built-in electric field, these ions would now drift due to the built-in electric field towards the interfaces again. And this is exactly what we measure. And this you can see here, for example, where we now have applied voltage, which more or less the built-in bias of the cell for 2 seconds in order to give the mobile ions enough time to redistribute. And then we go back to 0 volt, and then we measure this transient capacitance measurement. And what we see here is this, again, nicely changes with temperature. And we can describe this in this formula where we have a steady state capacity and the change, which is now dependent on the exponential function with the time constant in it. And again, this is related to the activation energy. So we can do this temperature dependent, place them on a Arrhenius plot and extrapolate activation energies. And as you can see here, this activation energies, which we obtained from both the time domain or the DC and the AC, which is the frequency domain, very similar, indicating already this is a very similar processes for this material. But now, how can we be sure that these processes are actually due to the migration of mobile ions? For this, we can look a bit more in detail about how we can distinguish between electronic and ionic defects. So, because these techniques are typically traditionally more used to quantify electronic trap states within materials. So if we now would assume here we have a trap state within our semiconductor. So here there's one band energy, which would be now the conduction band. And we have some, for example, an electron, and we have a certain trap state within the band energy. this electron can be trapped with a certain time constant, and then trapped, which means it's localized, and then it can again escape from this trap state with an emission time constant. How would we, in an experiment, try to determine these values? To measure this capture time constant, we would leave the cell at 0 volt or at for a long time, or we could also apply a negative bias if we want. And then we apply a forward bias. And that would mean that we reduce the depletion width. And if we have any traps within the material, we would fill all of these traps. And that would be now this capture coefficient. And if we now want to see the emission time constant, we simply would go back either to 0 volt or to a negative bias. And then we could measure how long it takes these trap charge carriers to escape. And if we look a bit on what kind of timescales we would expect for perovskites, the capture cross sections, which is the attempt to escape frequency. In the end, this is very fast, in the order of 10 to the minus 13 to the about of 10 to the minus 10 seconds. Whereas the emission timescale is now dependent on the trap energy with an exponential function. So this strongly depends on how deep your trap is. And if we now assume typical traps, which were reported for perovskites, from more or less 100 millielectron volts to, let's say, 0.6 millielectron volts here, we would have a very large variety of timescales. But if we look at these two, there's one clear trend that this is lower, the emission is lower than the capture, which is related to this exponential function which we have here. And now, how would this look for ionic defect states or mobile ions in this device? So if we do the same measurement procedure, where we first apply a bias and we have, let's say, no field at all within the perovskite, so again, flat band conditions, then the redistribution of ions would be mainly dominated by diffusion within the perovskite. And in the other case, where we again go to 0 volt or a negative bias, we would have an electric field. So in the most extreme case, this will be dominated by drift of mobile ions. Or in the reality, we always have a mixture between diffusion and drift. And if we look at the expected time scales, so the diffusion is depending on the distance and the diffusion coefficient, again, placing here typical values for perovskite, halide perovskite materials with thicknesses of a few hundred nanometers, we would expect diffusion timescales in the order of 100 milliseconds to tens of seconds. And for drift, this is in a similar timescale, but slightly faster, because we now have a built-in electric field. And there's again first of, if we compare this now to the timescales which we would expect for electronic defects, we see that now the timescale for diffusion is actually slower than the timescale for drift. So if we put these two together, for electronic defects, you would expect that this timescale to tau2 is much larger than tau1. Whereas in the case of mobile ions, it's the other way around. So they are much more similar, first of all, but then on the other hand, also the diffusion is expected to be higher than the timescale of drift. So this is what we, for example, did here for a perovskite material, where we now, with this transients measurement techniques, we can measure tau1 and tau2, and we can also, and then we can test if this is, and in what kind of range this is, and we find that this is above 1 and below V to kBt. So this is exactly in the range where we would expect it to be for diffusion of mobile ions. Whereas if it would be due to electronic defect states, it should be well below 1. And if we now compare this to what we obtained with impedance spectroscopy, first of all, they're in the same range, but with impedance spectroscopy, we can only measure one time constant. We cannot differentiate between capture and emission, for example, or drift and diffusion. We typically only measure the slower process of it or a convolution of both. So only with the transient measurements, we can now make the distinction and can say that this is indeed due to mobile ions. And here's a plot from Carsten Deibel, where he now tested this. So for different measurement procedures. So what I've shown you so far is always applying a voltage, measuring the capacitance response. but what for other measurement techniques? For example, in IDLTS, what is done, he applied a he applied a photon flux. So there's a light pulse, and sorry, in optical DLTS, there's a light pulse, and he measured the capacitance response. So it doesn't matter if you apply a voltage or a light pulse, the signals are very similar. What they obtain, the signals are very similar. Or in IDLTS, what is done, there's again a voltage pulse applied, but the current is measured. So it doesn't really matter if you measure the capacitance or the current. And the same is for impedance. If you measure normal impedance, or if you measure IMVS, where you apply oscillating light pulse, or IMPS, where you also apply oscillating light pulse at different voltage conditions, so at open circuit or short circuit conditions. All of these measurement procedures yield very similar results, and they are all lying on more or less the same line in this Arrhenius plot. So this strongly suggests that all the different measurement techniques which you can do, they're always relying on some kind of perturbation, which can be a voltage pulse, a current pulse, a light pulse, and measuring some kind of observable, which can be capacitance, it can be a current, it can be a voltage. They all show the same behavior. And this is very important now when measuring these materials, because these theories for different measurement techniques were developed for classical semiconductors. And you use these techniques to measure different processes, such as recombination or transport. But what we can show here is that all of these measurement techniques also measure mobile ions. So whenever you measure these mixed ionic electronic conductors, you have to be very careful on how you analyze your data, and if you actually see what you think you're seeing, or if it's indeed dominated by mobile ions in these cases. And now I want to show you some experimental results which we obtained for different perovskite materials using these techniques. So here, what I show you now is a change in capacitance as a function of temperature. So what does that mean? If you have a peak, either in negative or positive capacitance, that would mean you have some process. So for example, it can now be a mobile ion migrating or a trap state. In this case, we made sure that this is all to mobile ions. And we found 3 different components. For example, for MAPI, we have 1 negative peak, 2 positive peaks. And the nice thing about capacitance measurements is now the capacitance is also sensitive of the sign of the mobile species. So we have 2 different charged ion species, negative and positive. So we assigned these to iodide and metallimmonium. First of all of the sign, but also for the results which we obtained for the diffusion coefficients, which fit very well to what others have reported in literature. And then we can place this, so we can fit all of the data and place them on an Arrhenius plot. And what we see is that, again, from MAPI, we have metallimmonium migration, we have iodide migration. This seems to change somewhat across the phase transition from tetragonal to cubic for metallimmonium lead iodide. But how this does now change when we go to different perovskite compositions. So here I show you, for example, one for 50-50 bromide and iodide, so mixed halides. And there are a few things which you see. First of all, there's no positive capacitance. So this indicates that there's no metallimmonium migrating in this mixed halide systems. And this is also expected from theory, because the bromide lead octahedrals have a strong bond to the metallimmonium ions, which hinder the migration of these metallimmonium ions. And in addition to that, the lattice is slightly shrinked as more bromide you add in, the lattice shrinks, which makes it also more difficult for the metallimmonium to migrate. And in addition to that, we find now that we have 2 negative peaks. So this would indicate that we have 2 halide species migrating, which is also expected for this 50-50 composition. So we could say that one of them is iodide and one of them is bromide. And here, one more composition. So this is now triple cation mixed halide composition, more what is currently used for the more high efficient perovskite solar cell devices. And here again, we see only negative contributions and no positive contributions. So indicating this is again only the halides migrating within this device. And now we look a bit more into detail and what we have found for these devices. So here you see the JV characteristic of this device. And here you see the device geometry. So this is now PTAA and a perovskite and C60 BCP. And these have an efficiency of about 20%. And here is again this capacitance change as a function of temperature. Now note that this is now flipped. This is still a negative contribution from the graph before. And this is what we find if we apply this voltage bias for 3 seconds. And if we now analyze this data carefully by fitting all of the data with exponential decay functions and making sure that we have a good quality fit, we find that this is actually composed out of 3 different species with different activation energies, So how can we now be sure what this is? Is this now ions or is this electrons? So what we did here is we did the same measurement, but we applied only a voltage bias for 1 millisecond. And that means that in 1 millisecond, the ions would have not enough time to migrate, to redistribute. But if we have electronic traps, electronic charge carriers have more than enough time in 1 millisecond to fill all the traps and to escape again. So this would, I would argue, only corresponds to electronic traps, whereas this is always a combination between electronic and ionic traps. And what we find is this, on the Arrhenius plot here, that these time constants, which we obtained for only 1 milliseconds, kind of correlate with this third component here, shown in yellow. So with this, this strongly indicates that in this system, for example, we have 1 electronic trap present and 2 ionic contributions present. So the ionic again would probably be to the iodide and bromide, and then some electronic trap, probably due to the presence of halide vacancies within the perovskite. Now, I want to switch slightly. I want to show you where this migration, this mixed ionic-electronic conductivity of perovskites has also been used and has a nice potential. For example, by using it in batteries and lithium-ion batteries. So for this, I will briefly explain what a lithium-ion battery is, how it works. So in a lithium-ion battery, you have 2 electrodes. Then we have a cathode and an anode, where these are now the active materials. Whereas in the solar cell, we had our active material in the middle. We now have our active materials on the top and the bottom. And these are separated by an electrolyte, which can be solid or liquid. So during charging and discharging, what we do is we move these lithium ions between the anode and the cathode. And perovskites have actually been used, for example, as an anode, which is shown here, where these authors showed different perovskite materials by reducing the dimensionality from 3D, 2D, and 1D. They could use this as an anode for lithium-ion batteries with very high capacities. So this is now 600 milliamp hour per gram. And to put this into a reference, graphite, which is the most commonly used anode material at the moment, has 370 milliamp hour per gram. So this seems very good. And in fact, that this is so reversible is also very interesting because it is indicated this is actually completely decomposing during charging and discharging the perovskite. But due to low formation energy, it seems to be forming again as you cycle it. And in addition to that, it has also been used as a cathode. So this is work by Jaffe and Hema Busara, where they fabricated a 2D perovskite out of chloride and copper. And they could show that they get a decent voltage of about 2 volts, and they could charge and discharge a lithium-ion battery with a perovskite cathode. And what is probably the most interesting, at least for me, is that you now have a photoactive material So you can also photocharge this, this cathode. So here the authors use this perovskite as a cathode again, but now they showed that by illuminating the cathode, you generate a photovoltage, and this photovoltage can actually be used to charge your battery again, which is, it's very interesting. In addition to that, so perovskite showed that it can be used as an anode and as a cathode. There is work which has also used perovskites or anti-perovskites in this case to use it as an electrolyte even for lithium-ion batteries. So you could even think of a battery which is all made out of halide perovskites in the end. And now I will stretch it even slightly more, even though this is a photovoltaic symposium. I will talk very briefly about some of the work I've been doing recently. Unfortunately, I haven't had the chance yet to fabricate batteries based on perovskites, but I will do this soon. But I will show you something what I did on selenium. And since selenium is also a material which is used in solar cells, in fact, it was the first material where a solar cell was developed. I thought this still fits into this symposium. And this is what I'm currently working on. So these are thin film solid state batteries. So the process is how we make them are very similar to solar cells in a way. The selenium layer is evaporated, the lithium metal layer is evaporated, the lipon layer is sputtered. And these are all very thin layers in the order of a few hundred micrometers to a few hundred nanometers to micrometers. And what is interesting now there, selenium, first of all, it's photoactive, as it was one of the first material used in a solar cell, but it's also a very promising material as a cathode itself because it has very high capacities. So this is what we fabricated. So we fabricate these batteries, and we indeed find that these materials have capacities above 400 milliamp hour per gram. And this, again, to put it to a reference, state-of-the-art battery materials have capacities below 200 milliamp hour per gram. That is why there's a lot of interest in these materials to use them in batteries. And here I show you some cycling data. So again, the capacity as a function of different cycles. And what you see here is that there's a change from going from cycle number 12. There's somehow a change to higher voltage, to higher cycle numbers. And what happened here? Moritz replaced slightly the shadow mask, which was on top of this battery, which was stored in the glove box. So before it was completely in the dark. And here, this is even only glove box light. So and you see that this glove box light strongly influences the charge discharging of this battery. And that's why you also see this is already on top of ITO, which is not really a typical material used in batteries, but more in solar cells. So what we are currently working on is measuring these batteries at different light intensities. And without being able to show you much at the moment, I can already tell you that we find that, as we know, the electronic conductivity is strongly increased, but also the ionic conductivity is increased in this selenium layers. And this is very interesting because there are not many materials where the ionic conductivity can be changed by illumination. Perovskite is one of them, but there are very few materials where we know this is happening. And if we now look at the Coulombic efficiency, this would mean how much charge do we get out for all the charge we put in while charging and discharging the battery. We clearly see that during illumination, this Coulombic efficiency goes above 100% because this is a photoactive material. And we have some additional charges due to the illumination. Which is one beneficial point, but also we can potentially much fast charge this battery by adding light to it. And this is a very interesting topic in the solar cell and in the battery community at the moment. So with this, I would like to conclude. First of all, I showed you that in halide perovskites, we have ion migration, and this ionic responses often mask electronic defects. So if whether you apply a voltage bias, you apply a current bias, you apply a light pulse, the measurement observable, should it be current, capacitance, or voltage, they're all very similar. So one has to be very careful when measuring halide perovskites and what kind of analysis one applies to it, to also check if this measured signal is actually due to ions or due to charges, that electronic charges. And I showed you that these transient measurements, it can be capacitance or current transient measurements, can be used to quantify ion migration, but also can be used to distinguish between ionic and electronic defect. And then finally, I wanted to highlight some of the work showing that this mixed ionic-electronic nature of halide perovskites open up possibilities for exciting new emerging applications. One of them is lithium-ion batteries, as I showed some examples, but also memoristors or artificial synapses, for example. Finally, would like to thank the whole thin films and photovoltaics group at EMPA, where I'm at the moment located and I'm working, and all the people which have contributed to the work I've showed you in some way and another, as well as NWO for funding me with the Rubicon Fellowship, being able to still work on perovskite solar cells while actually being located in a battery group. And you all for your attention, and I'm looking forward to a discussion.